So today we have a particularly challenging problem. A neutron star has an orbital period of 1 second. So t equals 1. Calculate its density. So this type of problem might seem completely out of left field. Because, how would you even sort of go about solving it? There's just no way you would have enough information. And, honestly, I would understand if you were to say that we didn't have enough information to solve it. But we actually do have enough information to understand it, to solve it, I mean. So, first thing, we need to kind of get a conceptual understanding of what is happening. So, a neutron star is obviously a spherical object in space. So, we can assume it's a sphere, which is why we're using this equation right here, which is for the volume of a sphere. So then we can also assume that there is an object at the surface, just some part of the neutron star that's at the very, very edge of the star. And we're going to label that as little m, while the neutron star, the mass of the entire system, is big M. So those are kind of our assumptions that we're making before actually delving into this problem. You're going to need these equations here. And if you want to try solving it yourself, feel free to pause the video and try it yourself. So, let's get started. So we have F equals G big M little m over R squared, where our big M is going to be, again, the mass of the neutron star, and our little m is going to be the mass of some point orbiting it. And so, since this object orbiting it is moving radially, since it's in orbit around the neutron star, we can say that the force of gravity in this case is going to be equivalent to the centripetal force, which is going to be little m velocity squared over r. And beautiful thing about this, we can cross out the little m, and this is no longer equal. Okay, so after doing this, we have gm over r squared equals velocity squared over r. And if we want to, we can go ahead and cancel this further. So then we would just have gm over r equals velocity squared. Okay, so that makes sense. So now, how are we going to relate this to time? Because we know what the time is in seconds. So basically what we need to do is we need to use our radial velocity equations. So we know t equals 1, so we can just set this equal to 2 pi. We can set omega equal to 2 pi. So what that means is that our velocity is going to equal 4 pi squared r squared. And so using algebra, I'm just going to simplify this a little bit further. So our r squared is we're going to divide both sides by r squared. So we have gm over r cubed equals 4 pi squared. Perfect. So now what do? We seem to be kind of stuck here. Like, how do we get this related to density? Well, luckily, mass equals density times volume. So we have a gravitational constant times density multiplied by the volume of a sphere, because that's what this object, this neutron star, is going to be shaped like. So we have 4 pi r cubed over 3 all over r cubed. We're going to cross that out, multiply by the reciprocal of r cubed, and cross out both r cubeds. So that's some That's just some beautiful cancellation that occurs right there. Love to see that. Multiply this by uh, 4 thirds pi. Perfect. And that's going to equal 4 pi squared. So the 4's cancel, and also 1 pi cancels on each side. So now what we end up having is gravitational constant times density over 3 equals pi. And now all of these, except for d, are just numbers, so we can work with this. So d equals 3 pi over g. And now we're just gonna get a number out of that because g is our gravitational constant. And so what we end up getting from that, you can just punch that into your calculator and get an approximate, is about 1.413 times 10 to the 11th kilograms per meter cubed. So let's take a moment to just reflect on exactly the answer we got here. So does this make sense under the context? Well, for a value of density, 1.413 times 10 to the 11th kilograms per meter cubed, that's a massive density. And if we know anything about neutron stars, is that they are extremely dense. So this answer makes perfect sense under the context of the problem. That's always something you should be looking for, is if the answer makes sense not just mathematically, but also within the context of the problem. So it's very important to understand the kind of methodology that we just used in order to solve for this. Because not just any, combination of equations is necessarily going to give you, this kind of just perfect solution to a problem like this. It took me a lot of tries to find the right equations in order to get the proper cancellation that it would take in order to get this kind of answer. So sometimes it takes that, but once you find how to solve it, it just goes to show that it is extremely elegant. The solution works just so perfectly, and it's one of my favorite physics problems because of that. So I hope you enjoyed this one. Stay tuned for more of these. Leave any problems that you need help with in the comments, and I will do my best to solve them.